Bem.
Só compartilhar a tela com a apresentação dele, só um minuto.
Tá. Mas
No lento aqui.
tá lendo? O pessoal desistiu, será? Quem assistindo. Estava marcado meio-dia, já meio-dia. Será? Só
Para você transmitir,
Meu Deus.
entendeu? Vai passar para o canal. Então a gente sabe que o computador não
Bem,
porque a gente
eu só queria expor o sistema da internet que caiu.
ele não dá muito
Pode começar. Você vai lá.
Não, pode começar.
Então, bom, então é com grande honra que recebemos o Dr. Valerio Zupo, bolsista CAPES Sprint, pelo Programa de Pós-Graduação em Ecologia e Evolução da UERJ. Dr. Valerio Zupo completou seu mestrado em Biologia em 1984, com destaque, foi laureado, na Universidade de Nápoles, Federico II, com uma tese sobre cadeias alimentares de fanerógamus marinhos. Em 87, trabalhou no Conselho de Pesquisa Italiano, Italian Research Council, num projeto para estudar dietas de camarões peneídeos em aquacultura. Em 93, teve seu doutorado na Universidade Livre de Bruxelas sobre calorimetria de organismos marinhos. Em 94, ganhou o prêmio Fulfillment e trabalhou na Universidade de Tecnologia da Flórida, num projeto que visava investigar assembleias de decáptodos em Indian River Lagoon. A partir do mesmo ano, foi contratado como cientista da Stazione Zoologica de Nápoles, em Ischia, para avaliar a ecologia de comunidades bênticas com especial atenção aos fanerógamus marinhos. Em 2016, obteve outro doutoramento na sua carreira pela UK Open University, com uma tese sobre relações entre teias alimentares e a biodiversidade de comunidades nativas. Desde 2017, é professora adjunta da Universidade Federico II de Nápoles e ministra da disciplina de Gestão de Recursos Marinhos. Ele é presidente da Sociedade Internacional para a Reprodução e Desenvolvimento de Invertebrados e atualmente é cientista sênior na Estação Zoológica de Nápoles e Ischia e trabalha atualmente com ênfase em ecologia química e biotecnologia de organismos marinhos. Ele publicou cerca de 200 artigos científicos em revistas especializadas, livros e capítulos de livros. É editor de um livro sobre crustáceos e tem múltiplas cooperações internacionais com diversas universidades, entre elas Israel, Alemanha, Espanha, Bélgica, Estados Unidos, França, Portugal, Austrália e, claro, Brasil. Então, eu gostaria de agradecer muito, mais uma vez, a presença do Dr. Valério e pelo interesse para colaborar no nosso programa. Agradecer a todos os presentes aqui, inclusive, quem está tentando ser remoto. Agradecer a pós-graduação a todos que participaram do processo da bolsa do professor. E também, principalmente, com destaque a professora Eugênia Antonar, que é coordenadora do programa CAPES Sprint, através do PPGEE, por toda a ajuda e esforço para resolver todos os problemas burocráticos, que existiram vários problemas burocráticos, e a CAPES pela concessão da Bolsa CAPES Sprint. E ao Israel, que está, coitado, me ajuda demais, sem ele eu não conseguia nenhuma dessa tecnologia. Muito obrigada. Obrigada, professor. Sorry for the português.
I cannot repeat it, but good morning. Obrigado to have you here. I will try to make a short long.
Yeah,
Sorry.
I'm trying to now. It's not with the
Now we have internet, but we don't have the presentation.
your presentation. It's working on YouTube because it's remit from the computer. But
Yeah.
from here, it's not working now. But,
Yeah, but they should see.
yeah, exactly.
Ah, wait, something.
I know.
Tudo perfeito, chegou meia hora, não, foi tudo perfeito.
It could be worse. It could rain inside. But... Ponte computer. Semi-signal. Ah, semi-signal. Probably you must function and F3. Function F. I don't remember which F. I use make.
Tá ligado? Ana Luz.
Let me see.
Ele não tá.
Mas estava.
No, you must just switch this pro F7.
Function F7.
Yes.
For source.
You must change this.
Okay. This one.
This one.
Yeah. It's duplicated.
Abriu a apresentação, deixa eu ver, ele só aparece por lá.
Try the other.
Okay.
Function. No, function
Seven.
F7. Wait. Duplicar. Extender. Solamente segunda. Solamente segunda. Try solamente segunda. You can follow by that. Doesn't like. Pesquisando todas.
Uma coisa, vou trazer meu data show e meu computador.
O computador não adianta, que tem que ser nesse aqui.
Mas então,
Tá show, pode ser outro.
Now we must go again.
Oi!
Don't touch.
Need to be duplicated, otherwise you can.
Here,
But not working.
even I
Okay.
cannot see.
Okay, it's working.
Ok.
Okay, let's pray it works in the next few minutes. And we will talk shortly about messages. Our life is full of messages every day. We are in the information time, and now probably we are mature to understand that life is an issue of messages, and messages are vital for life. Communication. What is interesting to note is that communication, don't touch it. Communications start from cells and they go through ecosystems. Cells communicate, organisms communicate, ecosystems communicate, and even the simple presence of an organism somewhere, it's an issue of communication. You can see them. Seeing it is a signal for you to have some reactions. So even the simple presence sends us a signal that must be translated and must be transformed in an action from cells to ecosystems. I will be very brief here because the last part probably is the most interesting. So we will just summarize this information, stuff. In this presentation, we try to explore why do cell, organism, and ecosystem communicate. There is a reason, a vital reason. Is it important? What does chemical communication look like? I say chemical communication because, of course, communication may be visual, may be electrical. Why you touch?
Sorry.
But in my studies, I am especially involved in chemical communication. And you will see why they are so important. And how they are used at various hierarchical levels and influence even whole marine ecosystems. I study all this to understand if this can be used for biotechnologies, because very often we can use natural processes to produce new biotechnologies. Did you touch it? Doesn't go.
I swear that's not my fault.
Before?
Is that one?
Yeah.
Okay.
So very don't touch it anymore. Signal transduction, that is, signals emitted by an organism or a cell are then converted into a response. We start with cells now, very briefly, to reach ecosystems. Cell may communicate, of course, by direct contact, if the communication is to be short distance. They can communicate longer distance through some electric signals. They can even communicate, as I said, by their presence. For example, in the case of apoptosis, that is another strongly important, dramatically important process in nature, because by apoptosis they don't need to send signals. They just put outside the membrane a signal, eat me, and it is over. Or at a longer distance, they can go through electric signals or hormones, so chemical signals. And we can say the phases of cell communication can be very easily schematized. We may have different types of messages, but must be emitted by a cell, must be understood by another cell, because there is a receptor able to keep this message. The receptor often changes its structure according to the presence. Something is not going?
No, sorry. Is the internet.
Yeah, internet is going out.
It's just unstable, but it's
Yeah.
working.
And finally, transduction. This signal must be translated into a response. That is, I understand the message, and I interpret the message according to the situation in which I am. You will see this better for chemical communication, because the same signal can bring two different responses. According to Sutherland, there are 4 steps. So emission, perception, transduction, response. And this is all. Also, all organisms communicate, no? So from cells to organisms. Let's think about an invertebrate, a plane, a mammal. Normally, communication between or among organisms may be obtained through compounds. And we can say in chemical ecology that a single compound is like a word. So a plant can emit a compound that is a word, and this word has a significance for somebody. In some cases, the significance is bilateral, so the communication is between artichokes. Artichokes have a bitter taste. If you try to eat them, they produce bitter, and that is a communication for you. You understand, it's bitter, not good. Then you can act. You can boil the artichoke, and it is no more bitter because we are smart. Also, organisms are smart. But in this case, it's a communication between 2 organisms. In other case, there can be 3 trophies. For example, between among 3 organisms. That is the plant that is eaten by an organism called the enemy of that organism with a word saying, okay, come here and eat my enemy. In this case, the characters are 3, but they can be also more. in nature. So these are simple words. However, often words can be misunderstood. So in nature, for important processes, we don't like a single word. We need a sentence. So several compounds producing a meaning that is well characterized. And about this, you can think about your nose. Before I was thinking, I took a coffee this morning. And I smelled the smell of coffee. To be able to recognize a compound or a group of compounds, even for a single chimeric carbon. The clear example can be mint and curcuma, that is the same compound. They just have one chimeric carbon having a different spin, and you can immediately understand how different is mint from curcuma in your nose. So our noses are much more sophisticated than any machine. Sentences are often important for vital issues. You must decide if you can eat or not something, and you can die. Normally, your body wants a bouquet, what we name a bouquet, that is a sentence of chemical compound. And we reach more, that's why bouquet. There is an ecology of smells. Smells care, smells are very important in our lives. Much more important than often we would give to them. Normally, we think that our main, most important sense is visual. That is wrong. An example that I often do at university with students is this. If you see a pizza, a beautiful pizza, you see the pizza margherita with mozzarella, but you smell it and it smells like charcoal, you will not eat it. Even if your eyes says, oh, that's a beautiful pizza, your smell says, no, the taste is of carbon, and I don't eat. But when in Christmas, I don't know if in Brazil is the same, in Christmas we give to our babies small pieces of carbon that is made of sugar. So it has the shape of carbon, but the smell of a cake. And we eat it without any problem. So evolutionarily, our main sense is smell, not visual, not ear. And smells are important not only because the emitter may have a special reason to send you, in this case, the friend to say, okay, bring around my pollen, but also because in some case, a bad smell is a symptom of something that you should not eat. And it's not one compound, it's a bouquet of compounds. So this is the main theory of chemical ecology. And it may be applied to cells, organisms, or even ecosystem. There is a organism one that is the emitter. The emitter may produce or store a compound. This compound can be can reach a receptor and use it for some vital operations. In some cases, there is also an activity. That is, the signals travels in this sense, but the organism too is able to activate the production by organism one. And this makes a big difference between activated compounds and not activated, that is continuously produced by one organism, for example, a cell. So this is, from another point of view, the theory of severe chemicals. We can divide the compounds information in two groups, pheromones and allelochemicals. in the case of pheromones, we can have several types of compounds that are produced for sex, so within the same species, for aggregation. So there is a compound that pulls together several species, several individuals. Alarm pheromones, that means I am in danger, go away, Charlie Bravo, Charlie Bravo, and trail pheromones and so on. While allelochemicals are something that tends to make a damage to other individuals, to other groups of species, and also in this case, according to if they are the same species or other species, they are allelochemicals. So, in nature, as I said, we explore the surrounding world and sound, we think. But most animals, including us, give more importance to molecules. And if you see your dog, when it is going around in the street, you understand that also mammals give a lot of importance to this. A dog is able to, I'm sure, understand from that smell if from there was passing a male or a female. If it was a big dog, to avoid a small dog, to search for fate, and so on. You don't see it. We don't see it. But the compound is there and is more precise than any photo for a dog. So it's important the significance that the receiver attributes to that signal very quickly, because we will be slower in the last part. Here, the research is very young, because this research on odors started on terrestrial systems, and only since 10, 15 years in marine ecosystem, we are starting to use this type of approaches. Let's start imagining that marine animals live in an environment that is suffused with thousands of compounds. So, first of all, they must discriminate the important word among a lot of noise. And as I said, some words, these are semi-chemical infochemicals, may produce sentences for them. And we will see now some of these examples, especially those that can be important for biotechnologies. One important point, again, as a premise, is that the language may evolve, just like in case of our languages. So also chemical words and their meaning may evolve in time. Evolution brings organisms to respond. The communication in this case is long, sometimes millions of years, but during this evolution, the same compound may have a different meaning. For example, we will see better, but in the case of mash, Hippolyte, that is the one that you saw before, the green one, but we will talk about. Hippolyte eats a diatom, feeds on a diatom, and the diatom was producing a compound that was deterrent. So the first meaning of that compound was stay away from me. Now, after some 1,000 years, Hippolyte was able to change the meaning of that compound and attribute it the meaning it's spring, let's make sex. So it's totally different, and this explains how the evolution may change language in long time. In the case of copybots, it is different. Here, the evolution didn't change the term, but also here, we will show probably in the next. No, I don't remember. However, I can tell you. In the case of these copybots that were studied mainly by Adriana Ianor and other colleagues in Naples, a diatom, also in this case a diatom, produced toxic compounds to avoid the copepods to eat on them. However, this mechanism, long view, was not very effective because when the copepod was eating the diatom, the copepod was dying. And another copepod or another organism was arriving to eat the same diatom. So it's not a good defense. And the diatom had an idea in evolutionary terms. I will not kill you. I will kill your F1, your sons. In this case, your population, the copepod, will never burst, killing all my cells. It will keep down because all the larvae will be teratogenic, and no other enemies will arrive because you are still present, but in low quantity. So it is like a fertility pill in this case, reducing the possibility for copepods to reproduce. Also in this case, as you see, there is an evolution of the significance of this message. Defense compound. Until now, I have told you about compounds that have a meaning, especially in defense. Why? Because they are also the easiest to study, and also because several organisms, especially when they are not mobile, they have not big teeth, they cannot defend, produce this type of chemical weapons. For example, the bestial plants are known for their constitutive and activating chemical defenses. Why both? Well, in the case of constitutive compounds, it is very easy. I have it in my body. If you eat me, you feel the bitter or the bad smell, and I will keep you away. But this is very expensive. The activated ones are cheaper because you stimulate me to produce an activated compound. So in the moment you are trying to eat me, I will produce it. And this is the case of diamonds, for example, that I told you before. Because both in the case of the shrimp, we will see better, and in the case of the copepod, they are wind activated. That is, I, the diatom, live freely and just have in my body some ampulle separated, and they are there. I don't need a lot. But when you eat me, you will crush them, and from the mixing of both these group of compounds through the epoxidase pathway, I will produce a series of poisonous compounds. So this is activated. Several invertebrates are known also for producing chemical defenses. Some other invertebrates do not produce themselves the defenses, but accumulate what is present in plants that they can eat. A top predator that is actively doing this is Homo sapiens. For example, we use chemical ecology continuously by accumulating the compounds toxic produced by plants and use them against insects or against predators or for other purposes. So even we use the same strategy, although to us it seems such a clever stuff, very different from invertebrates. As I said, all this can bring us to biotechnologies, because compounds having a meaning in nature may be true to be useful for our own purposes. For example, several new drugs, and this is our field of research, were produced like ivermectin, cyclosporin, taxol from marine organisms. And so once we have understood the mechanism of action of these compounds, we can just produce them, sometimes modifying them to make them more effective for our purposes. Some compounds are used for ecological conservation, and this is more or less the scope of our course here, because we will try to find compounds that could be used to reduce the presence of allophilous species. And some compounds we will see are triggering specific physiological activities in animals and in humans. So we can divide this type of allochemical or semiochemicals in two groups. Some compounds just generate a behavioral change. You smell a flower, you think the smell is good, and you keep the flower in your house. You smell a dead animal and you run away because, especially for smell, for volatile organic compounds. Other compounds may instead produce physiological activities, like in the case of medicine. So we extract or we produce the same compounds. Now, chemists have always searched for these compounds in organisms. This is a very old story. The problem of chemists is that they work especially through large screening. No? They take 1,000 organisms, they pass them through HPLC, and they try to see if they have any activity on cancer cells. This is a very dispendious way to do. We work like directed by curiosity, because in chemical ecology, the research is driven by the effect that we see in nature. So we already see that there is an effect. We study an environment, we see that two organisms have a given relationship, and so we search directly for that compound without the need to screen 1,000 organisms for an activity that can be absent. This is, in my opinion, the power of chemical ecology. And now we go back to these two fundamental aspects of communication: defense and physiological regulation. A compound becomes an infochemical when a species learns to translate the message, learns. Of course, if I emit a compound, I am not directly understanding the effect that it will have on you. You must learn it on me. That is, I produce a venom, something poisonous, and you are the species eating myself. During the evolution, you can learn that that odor, that taste, that compound is dangerous. And from that moment on, your behavior will change because you have learned. But the same happens to cells. A cell learns how to use a compound by evolutionary steps. And so the cells learns that with that type of ABC receptor, it's useful to bring this compound inside to make some activities. And so various compounds, maybe pheromone, and hormone, may regulate the metabolism of another species in a given way. And here, this is necessary. I give just a few information about the basic influences. As I said before, there is an emitter and a receiver. And the receiver has some system to understand the signal. Now, in the case of what we name pheromones, they are excreted factors triggering a social response in the member of the same species. And this means that they are positive. They produce a positive activity both for the emitter and the receiver. So if I am a male of a species that needs to mate with a female, I can emit a pheromone, and if the female is in agreement, this can be, we can be both very happy because I have given the right signal. Allomons instead are released by an individual of one species, but it negatively affects the behavior of the life of another species. So it is of benefit for the emitter, but not for the receiver. And when allomons are the typical case of plants that produce through the roots all around some allomons, so avoiding that other plants grow too close to take too many nutrients for their cells. In the case of chiromons, it is just the contrary, because in this case is an interspecific interaction, but it is negative for who emits and positive for who receives. And this is strange. Why I should produce something that is negative for me? This is the evolution, because I was emitting this signal for any reason, but how to understand the